In this video, we'll be looking at the different equations of planes. So we have a vector and parametric equations for a plane. We also have a Cartesian equation, but that's for later on. Now, for the equation of a line in R3, we know that the vector equation is made up of R0, which represents the vector from the origin to a point on the line, and a direction vector. And that's enough for a line. But for the equation of a plane, to get that larger space, we actually need two vectors that are on the plane, and they have to be not collinear. So if you look at the sketch here, you're going to have two vectors. We'll call them vectors A and B, and they represent vectors that are on the plane. And then you have this other vector R0, which starts at the origin and then goes to any point on the plane. And that will be enough to define that plane. And again, it is the sum of those vectors. So for example, let's say we have vectors A and B. They can be multiplied by any scalar, but if it's just 1 times each of them, their resultant vector will be that diagonal on the parallelogram. And then if you add that with your vector R0, well, here you have them head to tail, so you have your triangle law, and there's your resultant. And that resultant will represent 1 point on the plane. But as you modify the lengths of vectors A and B, you'll be able to get every single point on that plane. And then if you take this equation and break it down into the x, y, z components, you'll get your parametric equations. So let's try our first example. A plane contains the points A, B, C. Determine the vector parametric equations. Okay, well, I know I need two vectors on the plane. And if I have 3 points, I can use a combination of any two to come up with one of them. So we have vector A, and I'm just going to use vector A as vector AB. So 2 minus -1, 0 minus 3, and 1 minus 5. For another direction vector, I'm going to use, let's say, AC. But I could have done BC, it doesn't matter. So -3 minus -1, 1 minus 3, and 4 minus 5. Okay, I checked those. They are not collinear, so they work. And then for that R0 vector, from the origin to any point on the line, I can use any of the points, A, B, or C. I'm just going to go from the origin to A. All right, and now I'm ready. So my vector equation will be R0 plus whatever parameter I want. So I'm going to use S for vector A and T for vector B. And there's your vector equation. And now let's split that off into x, y, and z. So x is going to be -1 plus 3 times s minus 2t. Y is 3 minus 3s minus 2t. And z is 5 minus 4s minus t. And in all 3 of these, parametric and the vector equations, s and t are elements of all real numbers. And now, if I want to determine a point on the plane, I can just pick whatever values I want for s and t. And I'm just going to say s is 1, t is 1, and let's see what we get. And I could also just use the parametric equations if I wanted to. So we'll have -1 plus 3 is 2, 2 minus 2 is 0, 3 plus -3 is 0, minus 2 is -2, 5 minus 4 is 1, 1 minus 1 is 0. Okay, well there you go. there's a point on the plane. But when you have your vector equation, this represents a vector, but it's starting from the origin. So that's why we can safely also treat it as a point. Does the point 20, -6, and -10 lie on the plane? This is going to be the exact same type of question as when we were testing to see if a point is on a line, except now we have two parameters. So we have to solve for s and t, and then we'll use our z equation as a way to check our work to see if the point is actually on the plane. So I'm going to set my x parametric equation, so from right here, equal to 20, and -6 equal to the y. And I mean, I can do elimination right now. Everything's nicely lined up. I even have my t's, even my s's matching, so I can eliminate for either one. Or I can move all the constants over to one side first. But you know what, I'm just going to do it from here. I will eliminate the s's, which means I'm going to add my lines. So we have 14 equals 2. The s's are gone. Minus 4t. That's 12 equals -4t. So -3 equals t. That's great. Now I want to solve for s. So I'm going to plug it into my top equation. So that's 21 equals 3s plus 6. Bring the 6 over and we have 15. And 5 equals s. So I know s equals 5 and t equals -3 will work for the x and y parametric equations because that's what we used to solve for them. So my check to see if this point is actually on the plane is using the z. So we have 5 minus 4 times 5 for s, minus -3 for t. If we get -10, then the point is on the plane. If we don't, it's not. So we have 5 minus 20 plus 3. Well, that gives us -12, which is not -10. So the point is not on the plane. All right, let's try some other styles. A plane contains the line that and the point P. Determine a vector equation that represents this plane. Okay, so we're not given 3 points as last time, but we're given enough. First of all, we're already given a direction vector. So I can use that as vector A. I know I need another direction vector and I need R0. Well, R0 is the easiest one. It would represent the vector from the origin to a point on the plane. I know 1, 0, 2 is a point on the plane because that line is on the plane. And I know this point is on the plane. So I'm just going to use vector OP. So 1, -5, and 3 for R0. And then for vector B, well, I can just find the direction vector from here to here. So that's what I'm going to do. 1 minus 1, -5 minus 0, 3 minus 2, to get 0, -5, and 1 as the other direction vector. And now we can put it together. R equals R0 plus S times 2, 1, 1 plus T times 0, -5, 1, where S and T are real numbers. Now let's determine the x-intercept of the plane. So where does the plane cross the x-axis? Well, we know every x-intercept will have this form. And if we already know that y and z are both equal to 0, we could use that to solve for the parameters s and t. So I'm going to start off by writing the parametric equations. X equals 1 plus 2s plus 0t. That's nice. Y equals negative 5 plus s minus 5t. Z equals 3 plus s plus t. Now, if I know y and z are both 0, I'm going to swap that in. And now I'm going to solve using substitution or elimination. Now, because my s's already match, that's great. I'm going to eliminate the s's. I'm just going to clean this up though. So I'll bring the negative 5 over. I'll bring the 3 over. And now I'll subtract. I didn't have to do that, but I needed to line them up anyway. The s's cancel out. Negative 6t. And for t, I am getting negative 4 over 3. And now let's see what s is equal to, because actually I don't even need t for x. I'm going to sub it in here. So negative 3 equals s minus 4/3. I'll bring the negative 4/3 over, so that's going to be negative 9 over 3 plus 4/3 equals s. I just got myself a common denominator, which is negative 5 over 3 for s. And now we can solve for that x-intercept. So these s and t values we just got are the parameters that will make both y and z equal to 0, which we need for an x-intercept. And now I can use this information to actually get the x value. So 1 plus 2 times negative 5 over 3. That's going to be, get a common denominator, 3 over 3 minus 10 over 3, which is negative 7 over 3. So therefore, the x-intercept is negative 7 over 3, 0, and 0. And there we have it. And you could do the exact same thing for a y or a z intercept, except you're using different parametric equations and setting them equal to 0 to solve for that third component. Next, determine the equation of the plane that contains these two lines. Well, if you know that the plane contains these two lines, you have two direction vectors and you have 2 points that you can choose from. I need both of the direction vectors, so I'll label this one as vector A, vector B, and then I get to pick which of those points I want to use. I'm just going to use the first one. I could have even found another direction vector using the 2 points that were given. But because I look at these direction vectors and they're not collinear, I can use them no problem. And I said determine the equation. So I'm just going to find the vector equation. And there it is. Didn't have to work for anything. The next example, similar idea. But now if we look at our two direction vectors, they're collinear, which means I can't use both of them. I can only use one. So I'll use this as vector A. But for vector B, I'm going to have to create another direction vector using the 2 points I'm given, and hopefully I don't get another collinear vector. So 3 minus 1 is 2, 4 minus 2 is 2, 0 minus 1 is negative 1. That works. We have two non-collinear vectors, and then I'm just going to use this one as R naught. All right, now our vector equation. 1, 2, 1 plus s times 0, 1, 2 plus t times 2, 2, negative 1. S and t are both real numbers. All right, finally, what combinations of information define a plane in R3? So let's see which ones do. If you have 2 points, is that enough to define a plane? Well, no, because if you have 2 points, all you're going to get is a single direction vector. That's only going to define a line. So that's a no. 1 point in a direction vector, again, that's only enough for a line. 1 point and 2 direction vectors, that's perfect. That's exactly what we need for a plane, as long as those direction vectors are collinear. 2 points and a direction vector, that's also okay, because from those 2 points we can come up with another direction vector. If we have 3 points, that's also great. We saw an example like that. Out of those 3 points, we can form 2 direction vectors. And finally, 1 point and a normal vector. Now this will connect nicely when we look at the Cartesian equation of a plane, but what do we already know about normals? A normal is perpendicular to a line or a plane. And if we're talking about the normal of a plane, I need a vector that is perpendicular to a plane. But how do I find a perpendicular vector? I need 2 vectors out of it. So if I had 2 direction vectors, I could find the normal, which means if I have the normal, I must also know 2 direction vectors, and then I have a point. So that works as well, because we need 2 direction vectors for the normal. And that's it for our vector and parametric equations of planes. So once again, you need 2 non-collinear direction vectors on the plane and a single point on it, or any combination that will provide you with those 2 non-collinear direction vectors and the point.